13 billion years ago, something was burning in the darkness that shouldn't have been able to exist. It glowed 100 billion times brighter than any single star has the right to shine. It sat wrapped in a shroud of gas, roughly the size of our entire solar system. And for years, every time astronomers pointed the most powerful telescope ever built at the early universe, this thing and objects like it kept showing up in the images, small, impossibly red, and completely unexplained. Astronomers had a name for them before they had an explanation. Little red dots. Nobody knew what they actually were. Now, for the first time, one of them has been identified. It isn't a star. It isn't a normal black hole either. It's something in between, a hybrid object astronomers are now calling a black hole star. And it might finally answer a question that has bothered cosmologists for years. How do black holes weighing billions of times more than our sun manage to form so early in the universe's history, when there shouldn't have been enough time for them to grow that big? Here's how they found it, what it actually is, and why one object 13 billion light years away might rewrite part of the story of how galaxies begin. Before we get to this specific object, it's worth understanding why little red dots became such a headache for astronomers in the first place. When the James Webb Space Telescope switched on and started returning its first deep field images, it wasn't just showing astronomers galaxies further back in time than anyone had ever seen. It was showing them a universe more crowded with strange, compact, intensely red objects than any existing model had predicted. These weren't rare anomalies tucked away in a single image. They kept turning up, survey after survey, scattered through the deepest fields Webb pointed its mirror toward. Hundreds of them, sitting in a narrow window of cosmic history between roughly 650 million and 1.6 billion years after the Big Bang. That consistency is what made them impossible to dismiss as noise or instrument error. Whatever these things were, they weren't a fluke. They were a population, common enough and strange enough that any complete picture of how galaxies and black holes formed in the early universe would eventually have to explain what they actually were. The discovery centers on an object astronomers have named MOAM BH1, spotted using NASA's James Webb Space Telescope in the constellation Cetus. The light reaching Webb's instruments left this object roughly 1660 million years after the Big Bang, meaning we're seeing it as it existed when the universe was less than 5% of its current age. The research was led by astrophysicist Rohan Naidu, and the findings were published in the journal Nature. Webb has been finding objects like this for a while now. Small, unusually red points of light scattered through its deepest images, present in the early universe in far greater numbers than anyone expected. Astronomers nicknamed them little red dots, almost as a placeholder, because nobody could confidently say what they were. The leading guesses were reasonable ones. Maybe they were young galaxies, thick with dust, the reddish color coming from starlight filtered through soot-like particles the way smoke reddens a sunset. Or maybe they were something closer to ordinary compact galaxies, just unusually bright for their size. MOAM BH. 1 is the object that finally let researchers test those explanations directly. Because for this one particular red dot, the light was so overwhelming that it drowned out its surrounding galaxy almost entirely. Astronomers weren't looking at a galaxy with something bright inside it. They were looking at nearly pure light from one single, extraordinarily energetic source. To understand why that mattered, it helps to understand what dust actually does to starlight, because that was the first explanation researchers had to rule out. When light passes through a cloud of dust, the dust doesn't just dim the light evenly, it scatters blue light more effectively than red. Light, the same optical effect that turns a hazy sunset deep orange, while leaving the blue sky comparatively unaffected. If MOAM BH1's red color came from ordinary dust, its light should have shown that same telltale signature. Blue wavelengths scattered away, red wavelengths passing through relatively cleanly. That's not what the spectrum showed. The object's light was bright at some wavelengths, and then dropped off sharply at others, in a pattern that didn't match dust scattering at all. Something else was absorbing specific bands of light in a very particular way, a signature closer to dense, mostly untouched hydrogen and helium gas than to the sooty dust grains that reddened galaxies closer to home. That left researchers with a genuinely strange puzzle. Whatever was producing this light had to be small, extraordinarily energetic, and wrapped in a gas envelope unlike anything in a typical young galaxy. The team spent months building and testing physical models that could reproduce the exact pattern Webb was recording, trying combination after combination of stars, dust, and gas, before finally landing on the one model that fit. A black hole, roughly 100,000 times the mass of our sun, actively feeding on surrounding material and generating enormous energy, all of it wrapped inside a dense envelope of hydrogen and helium roughly the size of our solar system. The black hole itself isn't glowing. Black holes don't emit light. What's glowing is the material falling into it, gas spiraling inward, heating up under immense gravitational stress, radiating enormous energy before it crosses the point of no return. Normally, that infalling material would sit in a relatively thin, flattened disk, visible to telescopes as a distinct bright point, but here the black hole appears to be embedded inside a much thicker, more diffuse cocoon of gas, dense enough to absorb and reprocess much of the light passing through it, the same way a star's outer layers absorb the fusion-powered light generated at its dense, energetic core. That's the origin of the name. From a distance, the object behaves like a star, a compact, glowing sphere radiating enormous light from within a gaseous envelope. But the engine producing that light isn't nuclear. Fusion, the way it is in every real star. It's a black hole, tearing apart infalling gas and converting gravitational energy into radiation on a scale fusion alone couldn't match. A star made of starlight on the outside and a black hole underneath. It helps to picture the scale involved because the numbers here are difficult to hold in your head without a comparison. A black hole 100,000 times the mass of the sun sounds enormous, and it is, but on the astronomical scale of black holes, it's actually considered relatively modest, closer in size to what astronomers call an intermediate mass black hole than to the billion solar mass giants sitting at the centers of large modern galaxies. What makes MOM BH1 remarkable isn't its size, it's its brightness relative to that size. A black hole this size shouldn't be capable of outshining an entire galaxy. The fact that it is suggests it's feeding on surrounding gas at an extraordinarily fast rate, converting infalling material into radiation with unusual efficiency, which is exactly the kind of behavior that would explain how a black hole this size could eventually grow into something far larger, far faster than standard models expect. That description alone would make MOMB H1 worth talking about. But the reason astronomers are genuinely excited goes further, because this object may help resolve a problem that has bothered cosmologists since Webb's earliest observations began coming in, the question of how supermassive black holes got so big so fast. Here's the problem in plain terms. Every large galaxy, including our own, has a supermassive black hole at its center, often millions or even billions of times the mass of the sun. Under standard models of black hole growth, building something that massive should take an enormous amount of time, as the black hole slowly accumulates matter over billions of years. But Webb keeps finding galaxies. With fully formed supermassive black holes already in place, when the universe was only a few 100 million years old, far too young under the old timeline for that kind of growth to have happened. That mismatch has been one of the most persistent puzzles in modern astrophysics. Either something is wrong with how astronomers estimate the age of these early black holes, or something is wrong with the standard model of how quickly black holes are able to grow. Neither option is small. Until now, nobody had direct observational evidence of what an early stage, rapidly growing black hole might actually look like while it was still in the middle of that growth spurt. Astronomers had theoretical models describing how this kind of rapid, gas-shrouded growth could work in principle. The general idea has circulated in astrophysics for years, usually under names like super-Eddington accretion, a term for feeding faster than the standard theoretical speed limit for black hole growth normally allows. What nobody had was an actual observed object caught in the act, with a real spectrum, real measurements, and real evidence, rather, than a simulation on a computer. That's the gap MOMB H1 fills. It's the difference between suspecting a mechanism exists and finally watching it happen. That's what makes MOMB H1 potentially so important. If black holes in the early universe commonly passed through a phase like this, deeply embedded in dense surrounding gas, feeding rapidly, disguised as something closer to a star than a black hole, it would help explain the puzzle in a completely different way. These black holes wouldn't need to grow unusually fast to become supermassive on schedule. They might simply be feeding far more efficiently than astronomers assumed, wrapped in exactly the kind of thick gas envelope that would let them pull in material quickly, while also making them look from a distance like faint red stars instead of the rapidly growing black holes they actually are. In other words, a puzzle that looked like it needed a strange new kind of physics might instead need a stage of black hole life nobody had directly observed before. This one. That's a significant claim, so it's worth being precise about what's actually established here and what's still being worked out. What's confirmed? MOM BH1 is a real object, observed and measured with Webb, with a spectrum that has now been published and peer-reviewed in Nature. What's strongly supported? Its unusual light output cannot be easily explained by dust-reddened starlight, and a black hole embedded in a dense gas envelope is currently the best-fitting physical model researchers have been able to build for the data. What's still being tested is how common this phenomenon actually is. A separate analysis released earlier this year identified over 200 candidate objects across Webb surveys that could represent the same kind of black hole star phenomenon, hidden in situ. The broader population of little red dots astronomers have been cataloging for years. If a meaningful fraction of those candidates turn out to be genuine black hole stars, once studied in the same detail as MONBH1, it would suggest this isn't a one-off oddity, but an entire hidden stage of black hole growth that's been sitting in plain sight, misread as something else, for as long as Webb has been taking pictures of the early universe. If it isn't common, MONBH1 stays remarkable in its own right. But the bigger mystery of early supermassive black holes would remain open, waiting for a different piece of the puzzle. That's the honest state of the science right now. One confirmed extraordinary object, and a much larger question about whether it represents a brief cosmic coincidence or a hidden chapter in how black holes across the universe actually grow. There's also a reasonable note of caution built into the discovery itself. Researchers involved in the work have described the picture as one that's still evolving quickly, which is a fair way to characterize any brand new category of object identified from a single clear example. Confirming that the broader population of candidates are genuinely the same phenomenon, rather than a mix of different explanations that happen to look similar from a distance, will take years of additional observation, spectroscopy, and modeling. Science regularly moves this way. 1. Unmistakable example, forces open a door, and then a slower, more careful process determines how much is actually on the other side of it. Either way, what Webb has captured is remarkable on its own terms. A signal that crossed 13 billion years of empty space to reach a telescope that didn't exist a decade ago, carrying the record of an object caught in a phase of its life that may only last a relatively short window before the surrounding gas clears and the disguise falls away. For a brief cosmic moment, a black hole wore the mask of a star, and astronomers happened to be looking at exactly the right patch of sky, at exactly the right time, to catch it. That's the story little red dots have been trying to tell for years, one faint red point of light at a time. Astronomers just needed a telescope sharp enough and a model strange enough to finally hear it. If black hole stars turn out to be common in the early universe, it wouldn't just solve one mystery. It would mean an entire hidden stage of cosmic history has been visible in Webb's images all along, waiting to be recognized for what it actually is. What you think astronomers will find when they check the next 200 candidates? Let us know below.